Okay, we've been talking about solutions and some solution stoichiometry. So remember, as we talked about, and we talked about kind of titrations, which really is solution stoichiometry. It really is, again, the same basic stoichiometry steps that we've been doing in any sort of process. We want to make sure that we balance the equation. We want to take whatever they sort of give us and convert to moles. We also always want to think about, is it a limiting reagent type situation? We then want to do our mole to mole relationship using obviously our limiting reagent if necessarily. And lastly, we want to take our moles to some other unit. Now, the main difference usually with solution stoichiometry is somewhere along the way, we usually will use molarity, and that's moles per liter. And if you use it up front, which is very common, we usually would, at this step, solve for moles, which would be liters times molarity. And again, that's a very common sort of spot where we would use sort of molarity. And the same idea as how we use sort of grams and molar mass from the periodic table to get to moles. This is, again, just a different way to get to moles. And also super common at the end here. A lot of times we may actually solve for volume of our solution, and that would be moles per divided by molarity. Or just straight up, you may be asked, what is the molarity of the solution? And at that point here, we just go into moles over liters. So in these type of cases, we typically use stoichiometry, especially in a titration type of calculation like we did the other day and talked about the other day. We usually have a known solution where we really know everything sort of about it, the molarity, the volume, and that's what really allows us, again, to get the moles of that particular solution. And we can use stoichiometry in the balanced equation to relate those moles to the moles of our kind of unknown solution. For example, like your acid in the titration that we did was sort of the unknown solution. Any questions on that there? All right, so we kind of started and stopped, I think, on this one. So let's go through this one here. And we're looking for what volume of 0.355 molar sodium hydroxide is required to react with 125 milliliters of 0.5 molar sulfuric acid. Again, this could be like a titration where you're adding, some sodium hydroxide to your sulfuric acid. So it is a solution stoichiometry problem here. Again, we got to start with our equation. So remember that when we're writing equations, the first thing we really want to do is make sure we have all the proper formulas. So we got sodium hydroxide, and that is a sodium with a +1 charge and a hydroxide with a -1 charge. Gives us sodium hydroxide. Plus our sulfuric acid. Sulfuric acid is no hydro, so it does have oxygen in it, and ic is replaced with 8, and that's sulfate, so that is H2SO4. And again, when you see this reaction, you should recognize it as a double, thank you, a double displacement reaction. It's an acid-base reaction. If you remember an acid-base reaction, we basically always get a salt and water are the two things that we get. That's a positive, negative, positive, negative. So we're going to switch partners here and go that way. And that is going to give us H2O. And remember that when we put together sodium, which is +1, and sulfate, which is -2, we end up with a formula that looks something like this. Again, because sodium +1, sulfate -2. So we need 0 charge when we put it together. So again, the importance of that, as we talked about previously, you want to make sure you got the right formulas. And then once you have all the right formulas, we do want to then make sure that the equation is balanced. And in this particular case, it is, bless you, it is not balanced. And we do need some coefficients here. And I believe we need a 2 there and a 2 right about there. And now we have a balanced equation in this case. So obviously, this is really important, especially if you have stuff in words, like you sometimes will in these type of problems. If you don't have that balance equation correctly, you're not going to be able to do, obviously, the calculation part correctly because you'll have the wrong sort of relationships. Now, if we just kind of survey what was given to us and what we're looking for, we are looking for a volume. We do have the molarity given to us here of sodium hydroxide. And for the sulfuric acid, we do have the volume given to us, and we do have the molarity given to us here. And once again, remember, we really want to start with the second part of stoichiometry, which is we want to convert to moles. And if you just look at this, this is the only information that will allow us to get to moles using our molarity. And if we look at the sodium hydroxide in terms of what we're trying to get to, we are trying to solve for the volume. We already have the molarity. So for the sodium hydroxide, we are missing the moles of it. And that is really where, again, the stoichiometry is going to come into play. We're going to allow us to use stoichiometry to figure out sort of the moles of sodium hydroxide, and that will allow us to ultimately get to the volume. So the goal here is we got to get to moles of sodium hydroxide. The only way we could do that is to start with what we could get to moles from, and that is the sulfuric acid. So we're going to convert our volume into liters, which it always needs to be when we are dealing with molarity. And that will give us 0.125 liters. We could also use our molarity really as a conversion factor, as we talked about. That is basically 0.5 moles per liter. Or if you needed to, you could flip it the other way when you're doing a dimensional analysis sort of calculation. So here we will start with the liters because we're ultimately looking for moles. And moles, again, is liters times molarity. So here we will flip we will not flip it, we'll keep the molarity exactly the way it is. Moles on top and liters on the bottom here of H2SO4. That's going to give us here 0.125 times 0.5, 0.0625 moles of sulfuric acid. This is essentially the first step in our stoichiometry calculation. This is the second step here, which is converting to moles. This is not a limiting reagent problem because definitely we cannot get moles of each reactant, so it's just a regular stoichiometry problem. So at this point, we're ready to do our third step, which is our mole-to-mole relationship. So we want to look at the two things we're interested in. H2SO4 is one thing that was given to us, and we want to look at what we're trying to find, which is sodium hydroxide. So from the equation, we can see for every 2 moles of sodium hydroxide, we got 1 mole of H2SO4. So here we'll continue on with our number. Using that relationship from the equation, we're going to go opposites cancel. So 1 mole of H2SO4 goes on the bottom. 2 moles of sodium hydroxide go up on top. And that's going to get us here, we're going to times it by 2 basically. 0.125 moles of sodium hydroxide. At this point, that is kind of the missing piece that we needed to find our volume of sodium hydroxide. So we could kind of do our fourth step here, which is we will use the molarity of the sodium hydroxide now. And again, just like before, we can convert that into 0.355 moles per liter. And again, we could flip it if we needed to. And in this particular case, we do need to flip it. So we're going to divide by the molarity of the sodium hydroxide. So 0.355 moles on the bottom per liter up on top. That's going to cancel. And we will end up with 0.355. About 0.352 liters, or if you times it by 1,000, about 352 milliliters in this case, yeah, of sodium hydroxide. So again, hopefully you can see it is again the same four steps. Balance equation, convert to moles using molarity in this case, mole to mole relationship, and convert those moles into some other unit, also using, in this case, molarity on the back end of the calculation. Like a normal stoichiometry calculation we've done before, you could obviously do all the steps all together in one calculation without getting answers in between. Again, if you do get answers in between, try not to round too much along the way. Any questions on it out there? All right, let's try one more here to wrap it up. If in a titration, it is required 63.5 milliliters of 0.375 calcium hydroxide to reach the equivalence point in a titration of 95.5 milliliters of hydrobromic acid. What is the molarity of the hydrobromic acid? So give it a go there, go through those four steps and see what you end up with. Okay, let's take a look, see how you're doing. So this is a titration problem. Really, again, titration problem is really just a stoichiometry problem. So you should just think about following the four steps that we normally do. Once again, here, very common, you're sometimes not given the equation, so we want to make sure we just start with the right equation. So obviously here we got some calcium hydroxide reacting with hydrobromic acid. Hydrobromic acid is HBr as it has hydro in it, which means it does not have oxygen. And calcium is +2 and hydroxide is -1, gives us CaOH2 as our other reactant. Again, this is basically an acid-base reaction, which means you should probably, in most cases, always produce salt and water. So water here, H2O, and that does come from, again, the H from the acid, the OH from the base on the double displacement and switch. And then the calcium and the bromine are going to come together. And once again, we do want the right formula. Calcium +2, bromine group 7 -1. Going to give us a CaBr2 as our other product in this case. At this point, we obviously want to make sure that it is balanced. Otherwise, again, it's not going to do us much good. And again, here we will need some twos going on, I think. And that should do it, I think, in terms of the twos in this question. Any questions on that there? So remember, acid-base reactions fall under double displacement reactions, which means positive guys basically just switch partners, right, to the other side. All right, so now we can kind of analyze the information given to us. And obviously for our calcium hydroxide, we definitely have the volume here. And we have the molarity, which once again, I'm just going to kind of convert into moles per liter so I can see both of the units. And we have 95.5 milliliters of hydrobromic acid required to reach the equivalence point. And we were looking for the molarity here, right? And molarity is moles per liter, so that is what we're looking for. Obviously, here we already have the liters part. So once again, what we're missing to kind of finish the problem is the moles of the hydrobromic acid. So again, that is really where stoichiometry is going to come into play. And at this point, once again, this is the only piece of information that's going to allow us to get to the second step of the stoichiometry process, which is to get the moles. So here we are using volume and molarity. So we do need to convert our, once again, volume into liters. So we'll divide by 1,000. Going to give us 0.0635 liters. And now again, we could kind of do our second step, which is convert to moles using the only information we could do that with, which is our calcium hydroxide in this case. We will start with our volume. We will use our molarity of the calcium hydroxide. And that's going to get us moles of calcium hydroxide, so 0.0635 times 0.375. Going to get us here 0.0238 moles of calcium hydroxide. Remember, again, like most stoichiometry problems, we're not interested in calcium hydroxide. We are interested in HBr, and we need to get to the moles of it so that we could get to the molarity. So again, we now want to do our third step, which is a mole-to-mole relationship. And from the equation, we see 2 moles of HBr equals 1 mole of calcium hydroxide. So that is what we're going to use to do that. So we'll take our number from above, 0.02381 moles of calcium hydroxide. We're going to do a 2 moles of HBr on top and 1 mole calcium hydroxide on the bottom. So it cancels. So we'll take that, times it by 2. 0.04763 moles of HBr. At this point, we're ready to kind of finish it out and get to our fourth step. And we are looking for the molarity. And molarity is the moles, which we just calculated, 0.04763, divided by our volume of our HBr. Remember, we do need to also convert our volume of HBr into liters as well. So 95.5 milliliters, 1 liter is 1,000 milliliters, 0.0955 liters. So 0.0955 liters gets us, let's see here. About 0.499, looks like. 0.499 moles per liter would be the molarity of our HBr. Or at this point, you could, if you wanted to, once again, kind of put the big M back in for the answer and just leave it as big M as well. So either way is fine. Any questions on that there? Yeah. How, and number 2? Are you talking about up here? Yeah. So remember that when you have 0, say 0.375 molar, that big M stands for moles per liter. So when you take this, the number always stays with the moles part, and it's always per 1 liter. That is the same thing as writing 0.375 big M. And I would again highly recommend that you kind of see those 2 units because again, it's a very common error that people make that they just forget about the liters part and they just think the big M is like moles and stuff like that. So they kind of forget about the volume part of it. But that's an equivalent. That's basically what the big M stands for. And the number always stays with the moles part. Other questions? Yeah. All right. Any questions on solution stoichiometry here? That should wrap up chapter 15. There is a section on normality. We're not going to worry about it or cover it. So no normality in that chapter. We're not going to deal with it. All right. We're going to go off to the next chapter here. Do that maybe. All right. Dare I say this is chapter 16 here. Second to last chapter of the season, believe it or not. Only one more to go after this. That's what they say. All right, so acid and bases here. We're obviously going to talk about both of those things and pH and stuff like that. So let's just start with sort of the idea of acids and bases. Acids were first recognized by their sour taste. It's common sort of acids like vinegar has acetic acid in it. Lemons have citric acid. What is sort of a basic definition of acids? It's really the ability, as we will see, of something to produce H plus ions in solution. So an acid is really something that when it goes into solutions has the ability to produce just free H plus ions floating around in solution and be able to produce that. And that's basically what an acid is. A base, on the other hand, is characterized by a bitter taste. Obviously, you shouldn't taste any acid or bases in lab. It also has a slippery feel. A lot of soaps, drain cleaners are bases. If you ever get a base on your hand, which maybe sometimes happens, It does feel very much like you have a layer over your hands and stuff like that. Bases are sometimes referred to as being alkaline, and a lot of our bases, or what is a base, as we will talk about, is really something that when it goes into solution has the ability to produce hydroxide. So when we see H plus, we associate that with an acid. When we see OH minus, which is hydroxide, we associate that with a base. As we will talk about, a lot of our strong bases come from group 1 and group 2 on the periodic table. Group 1 are the alkali metals. Group 2 is the alkaline earth metals. The word alkaline means basic. So a lot of strong bases come from group 1 and 2 that are hooked up with hydroxide, like sodium hydroxide, potassium hydroxide, as we just saw in that last example, calcium hydroxide. Those are where a lot of our kind of strong bases come from off the periodic table. Now, again, one of the kind of early definitions of acid and bases was one done by Arrhenius. And again, he said basically an acid is something that's able to produce hydrogen ions in solution. And as I mentioned a second ago, again, what we're really talking about here is the ability to produce these free floating H plus ions in solution. Not hooked up with anybody, not really attached to anybody, but just kind of freely floating in the solution. Now, one of the things that's really important about acid-base sort of chemistry, and when you're dealing with acids and doing acid-base chemistry, is a couple of sort of symbols that are used, or representations of acids that are used. So in acid-base chemistry, you will sometimes see H plus written. That is basically the same as another one that you commonly see, which is H3O plus. This is what is known as the hydronium ion. They are, for all intents purposes, the same thing. Yeah. So anywhere you see H3O plus, you could substitute it out with H plus and vice versa. So sometimes this would be represented as a bunch of H3O pluses floating around in the solution. And again, they're basically the same thing. I personally use H plus. Nowadays, a lot of books use H3O plus a lot in things. So again, anywhere in equations or formulas where there's H plus, you could substitute H3O plus. It's again basically the acid part of the solution. It's basically the same thing. So H plus hydrogen ions, hydronium ions are the same. And as we will later see shortly, H plus is also sometimes referred to as a proton in acid-base chemistry. And that is because hydrogen, as you hopefully remember, has one proton and one electron and no neutrons. And the only way you become positive is you lose an electron. So the only thing left is a proton. So H plus is sometimes referred to as a proton as well in acid-base chemistry. He defined again a base as we talked about a second ago, something with the ability to produce free floating OH minuses in solution. And as we'll talk about, really the ratio or proportion of H plus to OH minus in the solution is what determines whether or not that solution, for example, is acidic, basic, or neutral, that kind of relationship between those two things. So if you take hydrogen gas and you put it through water, you will get hydrochloric acid. And same thing with sodium hydroxide. If you dissolve it there in water, you'll get sodium hydroxide solution. So remember, naming wise, there is a difference in these two. This in the gas phase is referred to usually as hydrogen chloride. But if you remember when we talked about naming acids, they typically are aqueous solutions, and this would be hydrochloric acid. And obviously, we talked about naming acids, and depending on whether or not it has oxygen, right, as to sort of how you go about naming it. So the concept of Arrhenius was really a good sort of early step in sort of acid-base understanding, but it was limited. He did a lot of work with electrolytes, and a lot of the bases that he kind of did are used had hydroxide actually in it. And not all bases will have hydroxide actually in it. There are bases that are considered bases that actually don't carry hydroxide. So, for example, sodium hydroxide is a strong base, which will 100% break apart in solution into sodium ions and hydroxide ions, as it's a strong electrolyte and it's able to produce hydroxide. You can kind of think of it as it kind of carries hydroxide with it. So when it goes for a swim, it just kind of releases it in solution and you produce a bunch of OH minus really quickly. Now there's other bases, and this is a strong base, for example. There are other bases, say like ammonia, which is actually a weak base. And ammonia is a base because it does not carry hydroxide with it, but when it gets near water, it will actually steal a hydrogen from water. And the result of that is it will make NH4 plus, and that water will now be turned into hydroxide. So here it's able to produce hydroxide and is considered a weak base. If you remember when we talked about weak electrolytes, we had those arrows that head in both directions. And that happens here as well with something like ammonia, which is a weak base. It has the ability to produce hydroxide, but it's got to do a little work to do so, to produce it, and it will not produce anywhere near the amount of hydroxide in that solution if compared to sodium hydroxide, which again, sodium hydroxide just has to go in for a swim and it's just going to release that OH minus. Ammonia here has got to go find some water, do a little reaction with it to kind of produce the hydroxide. So that brings us to a more general definition of an acid and base, and that is the Bronsted Lowry definition of an acid and a base. And the Bronsted Lowry definition of an acid and a base is an acid is a proton donor. So an acid is a proton donor, which means it gives it away. Once again, a proton is referring to H plus. Yeah, so again, H plus is referred to as a proton. And a base is pretty much the one that's going to receive that. It's a proton acceptor, which again will receive the H plus. So the Bronsted Lowry definition, acid is the one that gives away the H plus, and the base is the one that accepts the H plus. Now, if you take a look at sort of the example I just wrote up there on the last slide, which was the NH3 example. This example here we can identify as sort of our Bronsted Lowry example. Once again, in this situation, we're going to send an H plus over. So in this situation, what's happening is the NH3 is accepting the H plus, and that's going to make the NH3, in this case, our base, because it's the one accepting the H plus. The water, in this case, is actually donating the H plus, and in this case, the water is going to be our acid. A consequence of the Bronsted Lowry definition of acid and bases is an important relationship actually happens. And that relationship is on the other side of the arrow, on the product side of the arrow, it actually creates partners to the acid and the bases. So the partner to the base on the other side is this guy. And obviously it looks just like kind of similar to the base there. And this is known as the conjugate acid. And the partner to the acid on the other side is this guy, which looks like it's similar. And that is the conjugate base. And what we create is this acid conjugate base pair where the only difference there can be is this difference right here, 1H plus difference between those things. As you go from NH3 to NH4 plus, that is one more H plus. And as you go from water to the other side, that is one less H plus. Stop any questions on that there. Now, a really important thing that people frankly screw up on a lot is people get the idea of the hydrogen, but they screw up on the charge. And to illustrate this, we could look at this example here. It is not only somebody losing or gaining a hydrogen, but they are also losing or gaining a positive charge. So when you lose a positive charge, you become one more negative because you now have more electrons than protons because you gave away a proton. If you gain a positive charge, you now become one more positive than you were before because you have now gained a positive charge. And we could see that if you just compare the difference between NH3 that gained the H, it became NH4, but it was neutral and it also became one more positive. So the charge changes as well as you go from conjugate pairs. And the same thing happens with the water. If you look at the water here, it is neutral. It loses a hydrogen on the other side and only has one hydrogen and one oxygen. And it goes from being neutral to now being negative. So it's really important that you understand the charges do change as somebody gives away a proton or donates the proton or accepts the proton. The charges do change on the other side. And then that's oftentimes missed by people in terms of when they kind of do these things. Any questions on that there? Yeah. So as I mentioned right there with our previous example, we do create these pairs on the other side of the arrow. And again, acid on one side, base on the same side, and then our conjugate partners, conjugate acid, and our conjugate base. By the way, you always find it this way, regular old acid and bases, left-hand side of the arrow, conjugate guys, right-hand side of the arrow. So conjugate partners on the right-hand side, acid and bases on the left-hand side. Once again, the only difference between them is a 1H plus difference, and it's that hydrogen that is being donated by the acid and accepted by the base. So that is the only difference for them to be pairs. So again, if we look at here, basically hydrochloric acid, uh, dissociated in water. This is going to be our acid. It's going to send the hydrogen over to water, which in this case, water is actually going to act as a base in this particular case, as it accepts the H plus, and it's going to create our partners on the other side. And there's our acid. This would be our conjugate base, and this would be our conjugate acid here. So you can see here in this particular case, the water is acting as a base. In the previous example, water acted as an acid. And there are certain things that could actually act as both an acid or a base, and water is an example of that. They are known as being amphoteric. They can act as an acid or a base. And an example is, as we see here, water. Or you'll see as well, typically anything that has a hydrogen, like a negative charge, like something like HSO4 minus, something like this, got a hydrogen and a negative charge, typically can also act as either an acid or a base because it has a hydrogen it could give away. And it also has the ability to sort of accept that H plus because it has a negative charge. So it kind of has room for a hydrogen to come back in. So it can act as an acid or a base. And those are typically things that you sometimes will see being able to do that. Any questions on that there? Say again? Are you talking about the HSO4 minus? Yeah, so if the it would not become positive. So if this guy, for example, did lose an H, we would take the H off and we'd be left with SO4, right? And when you lose that positive, you actually become one more negative. So it started at -1, right? So becoming one more negative from there would actually bring it to sulfate -2 in this case. If it gained the hydrogen, so if it accepted the hydrogen, and you put the hydrogen back on this, so like it gained that hydrogen, you would end up with two hydrogens, and SO4 -1 and +1 will equal 0 when you put it together, yeah? And then you'll be back to neutral in that case. Other questions? All right. So here again, just sort of an illustration of how we get to the hydronium ion. I'll write it up here since it's not cut off there. Hydronium ion. And again, that acid's donating the H plus. Now, earlier we talked about the idea that H plus and basically H3O plus is really the same thing. And you may be wondering, why in certain cases will maybe they use H3O plus versus just use H plus. And it really does sort of depend on how you write a particular reaction. So for example, if we look at this reaction here, which is really just hydrochloric acid, get rid of this here so I can write it. Hydrochloric acid, because it is a strong acid, it is a strong electrolyte. And basically when it goes into a beaker, it's just going to completely break apart into its ions 100%. So you'll get H plus and Cl minus. Now, to represent that sort of process, when it goes into sort of water, it is perfectly acceptable and is done a lot that you could just write the reaction like so. And this is just showing this strong acid, what is referred to as dissociating or breaking apart in water. And it's basically breaking apart into its ions like a strong electrolyte. You can also show this exact same sort of process of the strong acid breaking apart in more of like a Bronsted Lowry sort of equation and showing it with water in the equation. And you could write this exact same thing, and the exact same thing's happening in both equations. It's basically just the hydrochloric acid going for a swim in water, basically, and breaking apart. But in this situation, we would kind of show it in a more Bronsted Lowry thing where the H plus is coming over, and that is how we generate H3O plus and Cl minus. Both of these equations represent the exact same thing. They both represent just the strong acid breaking apart in water. One, you included the water in the equation, and one you did not. And the one where you did not, you just get H plus, and the one where you did, you get H3O plus, and these guys are basically the same thing. So they're basically just showing the same thing. And that's why they're interchangeable in acid-base chemistry, and it really just kind of depends on what you're trying to show or how you show that sort of dissociation of the acid. Not truly a super reaction or a real reaction going on in a sense. It's really just showing and demonstrating this acid breaking apart because it's a strong electrolyte. Any questions on that there? Now, I say, like I said, nowadays, a lot of times books will kind of always show the water in the equation, and you'll always kind of produce H3O plus. But for something like just showing the acid breaking apart is perfectly acceptable and fine to write it the top way. All right, so take a moment here. For each of these sort of pairs, what we want to decide is, are these pairs a Bronsted-Lowry acid conjugate base partners? So take a few moments there and decide for each of these cases. Thing that you should understand in terms of whether or not something is a Bronsted-Lowry conjugate acid base pair is this: the only difference there can be is that. Cannot be any other difference other than one H plus difference between the two things. So if we take a peek here at the first one here, we got HClO4 and ClO4 minus. And again, the only difference between these two is one H plus, which would mean that is going to be a pair. You could either put the H plus on the guy on the right and you get the guy on the left, or you take the H plus off the guy on the left and you get the guy on the right, right? So They are related to each other. If we take a look at the next one, we end up with HCl and ClO minus. The difference between these two is an H plus, but it's also a oxygen, right? Difference between them, which means they are not pairs because again, the difference is more than one H plus. And again, that can be the only difference that we see. We take a look at the next one here, H2PO4 minus and HPO4 2 minus. The only difference between these two is NH plus. Again, if you take off the H plus from this guy, you're left with one H, a PO4, and you become one more negative. So it started at -1, you end up at -2, and it is the same guy on the other side. So this would be. And lastly here, the only difference between these two is also an H plus, so that would be a pair as well. Any questions on that? So it looks like 1, 2, and 4 in this case are pairs. Any questions? Yeah. Say again? Yeah, so the relationship, depending on sort of what you're looking at, between if you're asking between these two guys, this would be the acid, right? And this guy would be technically, you would find it like on the other side of the arrow if you had it in an equation. That would be his conjugate base, if that's what you're asking. In that case, yeah. Other question? All right. So for each of these here, starting with each of these, write what the formula of the conjugate base would be. So again, starting with each of these, what would the formula of the conjugate? Okay, so let's take a look. So again, remember that the only difference in these things is an H plus. And the problem people sometimes have is, do I put the H plus on or do I take the H plus off? And that's kind of the important thing to try to figure out. So understanding the relationship of the sort of the Bronsted Lowry definition is important. That can help you figure it out. So remember, we have an acid and a base on one side of the arrow. And on the other side, we have our conjugate partners, our base plus our conjugate acid. And remember, the sort of relationship is the acid on one side is related to the conjugate base on the other, and the base on one side is related to the conjugate acid on the other. So when you approach a problem like this and it's asking you to write the conjugate base, what that means is you want to end up here. And that means that what you are looking at, if you think about it backwards, is each one of those things sitting there is an acid. And what you have to then do is think about the Bronsted Lowry definition of an acid, which is it should donate the H plus, right? And that's what you should do in this case. Because each of these are going to be an acid, we actually want to donate away the H plus. So we do want to remove the H plus in each of these cases. So if we do that, if I take an H off of this first one, and I'm left with an H and an S. Now remember, this thing was neutral to begin with, and it lost a positive charge, so it becomes one more negative than where it started from. Now, if I start with this guy, I'm going to also remove an H plus, and when I remove the H, I'm left with an S only. It is already at -1, and when you lose that positive charge, you become one more negative. So -1 and one more negative is a -2 in this case. Yeah. Here, I'm going to remove an H. That's going to leave me just two H's left, neutral to begin with. So when I lose that positive charge, I become one more negative, and we end up with a negative charge. And lastly, here, we're going to remove one H right about there. And when I do so, I'm left with one H, an SO3. Once again, this was neutral to begin with, which means when I lose the positive charge, I become one more negative. So again, as I was saying earlier, people sometimes get the H part of it correct, but kind of mess up on the adjustment of the charge as you do it. Question on those there. Now, speaking of those things that are amphoteric, You could have something like HCO3 minus. So why don't you write the conjugate acid for it, starting with that. Why don't you also write what the formula of the conjugate base would be? Again, in each case, you're going to start with this guy here, bicarbonate. Okay, so let's take a look again here. We're going to put on the H plus or take off the H plus. Let's start with the conjugate acid in this case. So if I want to end up at the conjugate acid, again, I could follow my relationship backwards. And that means in this particular case, it's going to act as a base. And the Bronsted Lowry definition of a base is somebody that will accept the H plus. So here we would actually be putting on the H plus as we go this way. We'll be adding that H plus. So when we add the H plus, we get two hydrogens, a CO3 plus 1 and minus 1 equals 0, and we become neutral at that point and make carbonic acid. Question on that one there. Now, in the second case, we're looking for the conjugate base, much like we did in this problem. And again, if we follow it back like we did in the problem, we see in this case it's going to act as an acid. So obviously this is something that is amphoteric, could act as an acid or a base. And an acid is somebody that will donate the H plus. So as we go this way, we want to get rid of that H plus. So we're going to take the H off, which leaves us a CO3. When we lose the positive, we become one more negative, and since it started at -1, we would then end up at carbonate with a -2 charge in this case. So if you come across a problem, which is sometimes common, they won't tell you, hey, these things are acids or these things are bases. They'll just say, write the formula for the conjugate acid or conjugate base. If you think about it backwards of what its partner would be, then you just have to use the Bronsted Lowry definition of an acid and base, and that will help you. Any questions? Okay. Let's talk a little bit about acid strength. And there are two types of acids. There are definitely strong acids, which are strong electrolytes. And there's also weak acids, which are weak electrolytes. And in a weak acid, we do have the reaction going in both directions because it is a weak electrolyte. And we do get those arrows, as we've seen with weak electrolytes, heading in both directions. In sort of a strong acid situation, we will get the one-way street heading towards the reactant product side and nobody coming back the other way. So if the forward direction predominates, that is a strong acid. And what it means is it is a strong electrolyte. It will 100% break apart in solution into ions. So hydrochloric acid, as we saw earlier, is a strong acid. It is a strong electrolyte. It is a one-way street. And when you have something like hydrochloric acid in a beaker or solution, it is 100% its ions. And there's no HCl units still together. It will completely break apart. That is frankly why it is a strong acid, because when you dump that in there, you're just going to produce a lot of free H plus really, really quickly, and it's going to be a very acidic solution in that case. What are some of our strong acids? There is a list of strong acids, which is a good list to kind of know. Because you could use this list to help you decide whether or not something is a strong acid or not, just by process of elimination. So hydrochloric acid is a strong acid, nitric acid is a strong acid, sulfuric acid is a strong acid, perchloric acid is a strong acid, hydrobromic acid, and hydroiodic acid. This list of 6 acids are your 6 basic strong acids. The reason why these 6 are good to know is if you come across anything else that's an acid that is not one of these 6, you could probably safely assume that it's going to be a weak acid. So these are, again, just as we continue on in chemistry or more classes, especially when you get into like 1B, knowing these are very, very helpful when you get there. Now, if we have the reverse reaction that predominates, we have a weak acid situation. So if we took something like hydrofluoric acid Hydrofluoric acid is not on this list, so I know it's a weak acid. It is also a weak electrolyte, which means when it breaks apart, it is going to mainly stay together, but will produce a little bit of these ions. So you'll get a little of these guys, but it is going to mainly stay together. So if you looked at a beaker of hydrofluoric acid, you would actually see a lot of HF units still together, but a little bit of ions in there. So since it's still able to produce some H plus in solution, it is still considered an acid, but again, it will produce nowhere near the amount of, say, like hydrochloric acid, because hydrochloric acid is just going to completely fall apart and release those H pluses into the solution super easily and going to create a lot of H pluses really, really quickly. So our weak acids, pretty much anybody that's an acid that's not on that list would be considered a weak acid and will mainly stay together in solution, but still produce a little bit of H plus, which again is why it's considered still a acid. Now, some relationships that occur when we talk about the Bronsted Lowry relationship, which is not super important for this particular class, but when you do go to like 1B, it is really important as well. The relationship is between sort of the acid and its conjugate base, or the base and its conjugate acid, is this. If it is a strong acid or a strong base, it will have a conjugate partner that's considered weak. And what that means is that partner basically will just sit there and not react with anything, and it's kind of neutral. If you have a weak acid or a weak base, its conjugate partner is going to be relatively strong. And what that means is if you have a conjugate partner that came from a weak acid or a weak base, it will actually go through a reaction known as a hydrolysis reaction, and it basically will be able to react with water. And when it reacts with water, it has the ability to change the pH of that solution. It can make it more acidic, it can make it more basic because it's reacting, and it's considered relatively strong. Now, there are some acids that can give away 2 hydrogens. There's some acids that can give away 3 hydrogens, and there's ones that can give away just 1 hydrogen. So these are sometimes referred to as being monoprotic, is 1 hydrogen given away. So like hydrochloric acid is a monoprotic acid. It releases 1 hydrogen in solution. Diprotic acid releases 2 hydrogens for di. Like sulfuric acid will eventually release 2 hydrogens and some sulfate. And there's a triprotic acid that can release 3 hydrogens like phosphoric acid. Will ultimately release a total of 3 hydrogens and phosphate. By the way, and we're not going to get into it too much here, but just so you know, a diprotic acid or a triprotic acid that can release more than 1 hydrogen, they actually come off one at a time. And so, for example, if you looked at sulfuric acid, the first thing that would happen is it would lose 1 H plus and make HSO4 minus. And that HSO4 minus would then lose a second H plus and make SO4 2 minus. So it actually happens in a sort of stepwise fashion. The hydrogens actually come off one at a time. They don't both just like drop off. And in fact, it's actually a lot harder to remove the second hydrogen than the first. And if you have something like phosphoric acid, which loses 3 hydrogens one at a time, by the time you get to the third hydrogen, it's super hard to kind of release that third hydrogen. And that's because you're building up a more negative charge every time you release an H plus, and you're trying to release something that's positive. So it kind of holds it a little bit tighter as you do it. By the way, that is why if you ever come across this in terms of Bronsted Lowry acid conjugate bases, are these guys conjugate base pairs? They are not, even though they are related to each other, because the difference here is 2 H pluses, right? Not 1. And as you go from here to here, that is a 2H plus difference, which means they are not considered pairs. And the reason for that is, as you can see here, as the hydrogens come off, this guy and this guy, those are pairs. The only difference between them is 1H plus. And then when this guy loses his second hydrogen, these guys and these guys are pairs. But as you try to go between these two, they are not considered pairs because, as you can see there, it's kind of 2 steps down the road. So it's too many hydrogens. So again, even though they are sort of related to each other because they do come from the same acid, they are not considered Bronsted Lowry acid conjugate base pairs because the difference is more than 1H plus. Yeah. Any questions on that there? And as you can see there, that HSO4 minus is what ties both of those things together. And that's why it's also an amphoteric substance, because if it donates, this guy right here, if it donates its H plus, it goes that way. If it accepts the H plus, it could go backwards that way. So again, that's why typically things that are amphoteric look like that. They have like a hydrogen, and they have a negative charge, and that's again allows them to give away a hydrogen or accept the hydrogen. And that's why there typically are those amphoteric type substances. All right. Now, water, as I mentioned earlier, is an amphoteric substance, and as we saw earlier, one case water acted as an acid, and in one case water acted as a base. So here, water acting as an acid, donating the H plus over, and on the bottom here, acting as a base and accepting the H plus. Water can actually react with itself. That is sometimes referred to as the autoionization of water. And one water is going to act as an acid, the other is going to act as a base, and we'll just say, hey, it's going to donate over. So that would be my acid, that would be my base, and it will make our conjugate partners on the other side. This is actually a reversible reaction, and it basically, you will see it with arrows heading in both directions, which is what that little arrow on top is supposed to represent. And it is a reversible reaction, forward direction and reverse direction. And that creates a relationship between those two things that is an important relationship, and that is what is known as Kw. And Kw is the equilibrium constant for water. That's what the K stands for. Capital K is an equilibrium constant. W is for water. It is equal to the concentration of H plus times the concentration of OH minus. And at 25 degrees, which is most often what you're going to deal with, it equals this sort of constant number of 1 times 10 to the minus 14. Now, the relationship between H plus and OH minus is an opposite relationship, which means as the concentration of H plus goes up, the concentration of OH minus goes down and vice versa. So as one goes up, the other goes down. So as the H plus goes down, the OH minus goes up. And by the way, the little brackets mean concentration. And most of the time, it is molarity that we're talking about when we see those little brackets. Now, this is a formula that you could use to figure out whether or not a solution is acidic, basic, or neutral. This is also a formula that you could swap out the H plus for H3O plus equals OH minus. They are the exact same formula. They are interchangeable. The H plus or H3O plus is the acid part of the solution, and the OH minus is the base part of the solution. So you could actually compare those two. If you calculate the H plus concentration and it's larger than the OH minus, that means in that solution your acid part is bigger than your base part. You would expect the solution to be acidic. If you calculate it and the H plus concentration is less than the OH minus, or the OH minus is bigger, the base part is bigger than the acid part, and that will be a basic solution. And if the H plus concentration equals the OH minus concentration, they both will equal 1 times 10 to the minus 7, and that will give you a neutral solution. So how do you use this to sort of calculate it? Well, it is the same calculation regardless of which one you're given. So if you want the H plus concentration, you're going to take 1 times 10 to the minus 14, which is Kw value, a constant, and divide it by the OH minus concentration. Or if you have the H plus concentration and want the OH minus concentration, it's the exact same calculation, 1 times 10 to the minus 14 divided by the H plus concentration. And then you could compare the two and see which one is larger. This is a very, very good reminder in this chapter that you definitely want to make sure you are using your exponent button properly in this chapter. So hopefully at this point you are punching things in scientific notation correctly in your calculator, but you definitely want to use the exponent button correctly here. Otherwise you will find your answers off by a little bit there. And you typically will know you're punching it in incorrectly is if you get an answer, front part of the answer looks good, but the exponent looks wrong. That is definitely a big indication that you're punching it in incorrectly in your calculator. So you definitely want to make sure to use the exponent button in this chapter.